AP Chemistry students. Today you're going to learn about organic chemistry. Yay! And there's a smiley face because organic chemistry is fun. So today we're going to tell you mostly how to name organic chemistry molecules and how to draw them. There's also more that you can learn about organic chemistry, but today we'll just touch on mostly how to draw them and how to name them. Hi organic chemistry students. This is a nomenclature for organic chemistry molecules. Nomenclature is the root of your organic chemistry molecule's name, and it's based off how many carbons are in your carbon chain. So this looks really intimidating, but it's really not. It's awfully easy to remember each one of them, and we will show you some easy ways how to. If you only have one molecule of carbon in your carbon chain, you use meth. If you have two, you use eth, and it keeps on going. Prop, bute, pent, hex, hept, oct, non, dec, undec, and dodec. And as you can see over here, another carbon is added to each chain as you go further and further. The nomenclature here is very important. Memorize all of these and you'll have a much easier time naming all of your organic chemistry molecules. Now we're going to go over memorizing tools for the AP Chemistry nomenclature. Here's an easy way to remember the first four because they're really kind of strange. You can remember them by remembering Michael eats peanut butter. Meth, eth, prop, bute. Named after Michael Tran, one of the first AP Chemistry students at Rockland High School. After the first four, it's actually really easy to remember the nomenclatures. Pent is in pentagon. Hex is in hexagon. Hept, well, I'm not sure if there's such thing as a heptagon, but let's pretend that there is and say that's 7. Oct is in octopus or octagon. Non sounds kind of like 9. Dec is like a decade, and then undec and dodec are just adding 1 or 2 to dec. Now we're moving on to the functional groups of organic chemistry. The three simplest of the functional groups for organic chemistry are alkanes, alkenes, and alkynes. This is when you have a single bond, a double bond, or a triple bond in between carbon molecules. Typically carbon molecules have only single bonds between them, but some molecules will have double or triple. For alkanes, you add the suffix "ane" to the end of the nomenclature root that we talked about before. For enes, you add "ene" to the end of it, and for alkynes, you add "ine" to the end of it. And there's some easy formulas to help you figure out how many hydrogens will be in the compound. You just take the number of carbon molecules and multiply it by 2 and add 2 to it. For alkanes, for alkenes, you take the number of carbon molecules and multiply it by 2 to find the hydrogens. And for alkynes, you multiply the carbon number by 2 and then subtract 2 to find the number of hydrogens in it. For an example, we're going to use the root prop to show you the difference between alkanes, alkenes, and alkynes. Remember, prop is the same as peanut, which means that there are 3 carbons in the molecule. For propane, there's a single bond, which you can see highlighted there in the red. For propene, we now have a double bond, which you can see in the red there. And for propyne, there's a triple bond there. As you can see, for each molecule, there's a certain amount of hydrogens. If you did the formula for each of them, then you would see that there's 1 less hydrogen for each because you need to satisfy the octet rule for carbon. Now we're back with some more functional groups for organic chemistry. Here are esters. These organic chemistry functional groups are now going to get more complicated than the alkanes, alkenes, and alkynes that we just saw. Esters have a suffix of -ate, and the R's there that you see in red are normally more carbon atoms. Over here we have the carboxylic acids. The prefix is carboxy, and the suffix is oic acid. So you have an OH off of one side of the O, a double bond O, and an R, which is probably another carbon atom off the side. And then here we have the acid halides, where the suffix is ol halide, and for here you have a carbon with a double bond oxygen off the top, an R, which would be another carbon molecule, an X, which has to be a halogen. That's what makes it an acid halide. So another functional group are the amides, with the prefix of carbamide and the suffix amide. Here you have a carbon bonded to R, probably another carbon, a double bond to the O, and a single bond to NH2. Here you have nitriles. The prefix is cyano and the suffix is nitrile, where you have a carbon double or triple bonded to nitrogen and single bonded to R, which is another carbon molecule. Aldehydes have a prefix of oxo and a suffix of al, and they're bonded to another carbon or the carbon is bonded to another carbon on either side and double bonded to oxygen above. For ketones, the prefix is oxo and the suffix is -one. You have a carbon atom bonded through single bonds to R on either side, which is another carbon atom, and double bonded to O on the top. For alcohols, you have the prefix hydroxy and the suffix -ol. It's where you have a carbon atom bonded to an OH. And this is the easiest functional group for me to remember because the OH just tells you every time that it's going to be an alcohol. For amines, the prefix is amino and the suffix is amine, where you have R, a carbon atom, bonded to NH2. For halogenos, the prefix is halo, and it's where R, a carbon atom, is single bonded to X, and X has to be a halogen, hence the name halogenos. For alkyls, the prefix is alkyl, and it's where R, a carbon atom, is bonded to an alkyl. Over here, common alkyls are methyl, which is CH3, ethyl, which is CH3CH2, and propyl, which is CH3CH2CH2, and then butyl, which is CH3CH2CH2CH2. Now we're going to do some examples of organic chemistry molecules. Here we have 2-pentanoic acid. You might think, whoa, look at all those colors, that's too much. But here, we'll break it down for you. Pent means that there's going to be a 5-carbon chain. You see them in blue down the middle. N shows that there's going to be a double bond somewhere in between the carbons. 2 tells you that it's going to be in between the second and the third carbon atom. There's a double bond. And then oic acid tells you that it's a carboxylic acid, which is where we add an O and an OH to the end of the molecule. All the rest of the bonds in between the carbons are single bonds, and you satisfy the octet rule by adding hydrogen atoms off of all the other carbon atoms. Another example is ethanol. Eth is eats, as in Michael eats peanut butter, which means that there are going to be 2 carbon atoms. Right there is your 2-carbon atom chain in blue. An means that there's going to be all single bonds between the carbon atoms. There's only 1 because there's only 2 carbon atoms, so right there is your single bond. And all means that it's going to be an alcohol. Here at the end, you see the OH coming off of the carbon, and then the hydrogen atoms come off of the other spots on the carbon atoms to fulfill the octet rule. For our third and final example, we have 2-ethylhexane. We're going to start here with the hex, which means that there's going to be a 6-carbon chain down the middle, as you can see right there. And then ane means that it's going to be all single bonds between the carbons, as you can see highlighted in red in between each atom. 2-ethyl. Ethyl is a common alkyl group, and 2 states that it's going to be coming off of the second carbon in the chain. Ethyl is CH3, so the C comes off of the carbon, off of the main carbon from the main chain of carbons, and then the H's come off of that carbon. To satisfy the octet rule on all the other carbon molecules, H's come off just like any other molecule. Congratulations! You made it to the end of our organic chemistry video. We hope you learned something and hope that this helped. Thank you for watching. This is made by Allison Jones, Makenzie Morton, and Eveline Gibson.